This is part 8 of the series of presentations about the best methods for converting aldehydes into secondary alcohols. This video is about the use of silyl enol ethers as carbon nucleophiles. These can be prepared from aldehydes, ketones, esters, amides, and other carboxylic acid derivatives. Most silyl enol ethers are stable and can be isolated and stored. The most common procedure for the preparation of silyl enol ethers is the treatment of ketones with a trialkyl silyl chloride or triflate in the presence of a weak base and a polar solvent. A more exotic strategy is the use of vinyl silanes as silylating reagent in the presence of a ruthenium catalyst. Silyl enol ethers can also be prepared by isomerization of silyl allyl ethers, whereby mixtures of cis and trans isomers are usually obtained. Another strategy is the reduction of alpha-beta unsaturated ketones with silanes. Finally, diastereomeric mixtures of silyl enol ethers can be converted into pure C-trichlorosilyl enol ethers by treatment with silicon tetrachloride. Unlike ionic alkali enolates or boron enolates, trialkyl silyl enol ethers do not form a closed cyclic transition state upon reaction with aldehydes, but an open chain transition state. Moreover, trialkyl silyl enol ethers do not react spontaneously with aldehydes, but usually require some catalyst, such as a Lewis acid. Trialkyl silyl enol ethers can also be converted into more reactive trichlorosilyl or trichlorotitanium enol ethers, which react with aldehydes through a cyclic transition state without any additional catalyst. Compared to ionic enolates, the advantages of silyl enol ethers are that these are not basic at all and can react with aldehydes under mildly acidic reaction conditions. These mild conditions cause fewer side reactions and high yields of alcohols are often attainable. Moreover, the diastereo and enantioselectivity of these reactions has been thoroughly investigated and highly stereoselective procedures are available. Main disadvantages are that, like boron enolates, this chemistry is not as inexpensive as catalyzed aldol additions, and sometimes low temperatures are required, what can be difficult to realize on a larger scale. These are two rare examples of uncatalyzed aldol additions of silyl enol ethers to aldehydes. Both reactions were run at high pressure and for several days, and only the reactive cyclohexanone-derived enolate gave a high yield of aldol products, as mixture of diastereomeric silyl ethers. The less reactive propiophenone-derived enolate, however, only yielded 25% of aldol products. These experiments show that silyl enol ethers are much less reactive than boron or alkali enolates. In this example, 5% of a weak Lewis acid was used to catalyze the addition of an acetophenone-derived trimethylsilyl enol ether to various aldehydes. The reaction already proceeded at room temperature and was complete in 2 hours with cinnamic and aromatic aldehydes, but was much slower with aliphatic aldehydes such as octanal. Much more reactive than trialkyl silyl enol ethers are trichlorosilyl enol ethers because these form a covalent silicon-oxygen bond with the aldehyde, what leads to a cyclic transition state and an intramolecular CC bond forming reaction. No additional catalysts are required. In this example, a sterically demanding tris-trimethylsilyl enol ether was used as nucleophile, and the aldol addition was catalyzed by a small amount of an imide. Despite the open chain transition state, a high diastereoselectivity was attained, probably because of the strong steric repulsion of the bulky silyl group. This is an instance of aldol addition of a propiophenone-derived silyl enol ether catalyzed by a chiral enantiomerically pure iron II complex. Both a high yield and high stereoselectivity were attained. Still more impressive is this example. Here, a sterically undemanding triethylsilyl enol ether of acetaldehyde was added to 2-thiophene carbaldehyde in the presence of 0.5% of a bulky enantiomerically pure Brønsted acid. Both a high chemical yield and an astonishingly high enantiomeric excess were achieved. So, what can go wrong? As in all aldol additions, the main side reaction is the elimination of water from the product. Electron-rich alkenes, such as enamines or enol ethers, sometimes undergo thermal 2+2 cycloadditions to electron-deficient alkenes or alkynes. And this type of reaction has also been observed with silyl-enol ethers. And as we already saw with boron enolates, also during the preparation of silyl-enol ethers, occasionally carbon is silylated. Although most enolates add to the carbonyl group of alpha-beta unsaturated aldehydes, Michael additions can sometimes occur. Finally, some electron-rich silyl-enol ethers may react with oxygen and must be kept under inert gas to prevent oxidation. This here is a short selection of some more examples, but many more have been reported. Because of the mild reaction conditions and high yields attainable, this strategy is often used in multi-step preparations of complex target compounds. The next video is about catalyzed aldol additions between two aldehydes, which are less predictable than the reactions of isolated silyl-enol ethers, but much less expensive and wasteful, and therefore better suited for large-scale preparations. See you then.